With Laplace transforms, the idea of a function being of exponential order is important to know that a Laplace transform does exist. And all that means basically is that a function can grow fast, it can grow exponentially, but it can't grow faster than exponentially. And formal definition, we have that the absolute value of the function is less than or equal to a constant times an exponential, and that's going to be for all t bigger than some number m. And so we have to figure out what k is, a is, and m is in these problems. And so if we take as an example trigonometric functions, sines and cosines, if we take f of t, let's take it to be sine of t to the fourth power. I mean, we know that t to the fourth grows fast, not exponential, but it grows fast. But that doesn't matter in this case because in this case, the sine function always has values less than or equal to 1 in absolute value, always between 0 and 1. And so this is going to be 1 times e to the 0t. And again, that's going to be for all t bigger than 0. So we have k equals 1, a equals 0, and m equals 0. And so we have exponential order. Another example here then is if I take a function that is an exponential function, then let's put in a sine of 4t as well in there. Now again, this part here is bounded always between -1 and 1, and this part is always positive, but this is always going to be less than, or the absolute value of this function is going to be no bigger than, well, e to the 3t times 1, because that sine term is always going to be between -1 and 1. Absolute value is between 0 and 1. So the biggest it could ever be, this function could ever be, is e to the 3t. And so now I have k equals 1, a equals 3, and m is still 0 in this case. And last example I want to look at here, if I look at a function that looks like e to 4e to the 5 times t to the 3/2 power, all right, what I'm going to do here is I'm going to look at the limit as t approaches infinity of my function divided by e to the at, right, my general exponential that I'm comparing against. And what I'm going to have here then is the limit as t approaches infinity, 4e to the 5t to the 3/2 over e to the at. And by properties of exponentials, this is the limit as t approaches infinity of 4e to the 5t to the 3/2 minus at. And the thing to observe here is, what we need to have for an exponential order function, this limit needs to be finite. And the point here is that regardless of how big a happens to be, that t to the 3/2 is going to grow faster. I can factor out a t from this. And for any fixed value of a, 5 times the square root of t is going to be bigger than a. And so that is going to be positive for 5 square root of t bigger than a, right, which is going to mean t bigger than a squared over 25. And in particular, then, it's positive, then it keeps getting bigger, and so this is going to go to infinity for any a. And since there's no a that makes this finite, this is not exponential order. The good news is that we don't see functions like this very often. We haven't seen a function e to the 5, t to the 3 halves whole semester. Most of our functions look like exponentials, e to the rt, maybe multiplied by a sine function, possibly even multiplied by a polynomial. And polynomials grow slower than exponentials as well. So any polynomial is also going to work. And that could be, I'll do one more example then, I guess. If I take f of t to be t cubed times e to the 3t. If I take this and divide by e to the at, I have t cubed times e to the 3t minus at, or t cubed e to the 3 minus a times t. All right, and I'm trying to show that this is a finite limit. And what I'm going to need to do in this case is I'm going to need to write this as t cubed over e to the a minus 3 times t. Switching the sign of the exponent when I'm bringing things to the denominator. And so here in this case, if I take now the limit as t approaches infinity of this function divided by e to the at, that's this limit as t approaches infinity of t cubed over e to the a minus 3t. And so this is going to be infinity over infinity if a is bigger than 3. If a is bigger than 3, this is infinity over infinity. So I'm going to use L'Hopital's rule. And the derivative of t cubed is 3t squared. The derivative of the exponential is going to be a minus 3e to the a minus 3 times t. That's still of indeterminate form, infinity over infinity. So I'll do L'Hopital's rule again. And I've got 6t over a minus 3 squared times e to the a minus 3. That exponential is still getting big. 6t is still getting big, so I still have one more L'Hopital's rule I can use. And the limit as t approaches infinity. Now I've got 6 over a minus 3 cubed times e to the a minus 3 times t. And now the numerator is just a constant. The denominator gets very big, and so this is going to be 0. Okay, and so because this limit is finite, this is again for a bigger than 3, we can, because this limit is finite, then f of t is of exponential order, and it has a Laplace transform. Okay, and the next videos we'll talk about how to find that Laplace transform. But this is some examples here about